Hi everyone, welcome to Great C++ Features in 10.3 as part of Code Rage 2018. My name's David Millington. I'm the C++ Project Manager here at Embarcadero. And just by the way, you're always welcome to email me. It's david.millington@embarcadero.com. It's always really good to hear from customers and C Builder users. So Red Studio 10.3 came out a couple of weeks ago. This is the splash screen. I hope by now many of you have already installed it. We're going to look at a number of great C++ features, many of which are only available in 10.3 in the new compiler that we have in 10.3. So here's some background information about it. C++ Builder uses Clang-enhanced compilers. Now Clang is an open source C++ compiler project. It uses LLVM. Now we take that and we extend it with our own language extensions. Now in C++ Builder 10.2, which is the old version, we supported only C++ 11. Now C++ 11 is a very important version to support. It's the start of what we call modern C++, where the C++ language has evolved and added some fantastic features. But in 10.3, which came out a couple of weeks ago, we now support C++ 17. That's the 2017 version of C++ for Win32. And this adds a whole heap of fantastic changes and tweaks to the language, and those are, well, some of those are the ones that we'll be looking at today. Now the 10.3 compiler for Win32 supports C++ 17. That means it also includes C++ 14, so we can look at some of the features that were introduced in C++ 14 as well. And it also includes, as part of that, a very recent edition of the Dinkomware STL. If you use Win64, you also get many of the benefits and features of that. So today is just going to be a light overview of a few of my favorite recent changes to C++. C++ 14 and 17 have introduced a lot of new features. This is just going to be a light overview of just a few things that I think are really cool and worth looking at. And those will be, we will dig into constexpr. Constexpr is really useful, something you may have heard of before. We're also going to look at structured bindings. We're going to look at the expansion of auto, and we're going to look at just a miscellaneous bunch, a hodgepodge of smaller miscellaneous features. Let's start by digging into constexpr. Now constexpr was added in C++ 11. We had mixed support. We have full support now in our updated compiler in 10.3. And constexpr has actually been expanded with its capabilities since C++ 11. So using the C++ 17 compiler in C++ Builder 10.3, we will let you experiment with everything that I show you today. So many people ask what constexpr is, and I think a good approach to understanding that is to regard it as a good way to achieve compile time optimization. Well, that's not necessarily true. It's really a guarantee of a compile time expression, but a really good and a really common way to use it is for compile time optimization. The situation is that compilers can calculate and optimize at compile time. They often do. But constexpr indicates that it must calculate a value at compile time. Now there are a few caveats there, and there's a bit of small print on the slide which I'm not going to get into. But for a constant expression, it guarantees that for a constant expression, it must be evaluated to be calculated at compile time, and it's compile error if that's not possible. So to dig into that a bit, here's an example of some pretty straightforward and quite common code. It's a method to convert degrees to radians, and this is the kind of thing that you might have in your application. And we call that degrees to radians, passing in a constant value of 42, which is a double. Now, because you pass in a constant value here, it is possible to calculate what 42 degrees is in radians right now at compile time. And many compilers will do some degree of optimization here. For example, they might inline the method. But of course, since you're passing in a constant value, and since this method here is what we call a pure function, for a single input it has a guaranteed single output, it can be evaluated wholly at compile time. And so the entire call of degrees to radians 42 could be replaced with the actual answer. But the question we ask is, will it be optimized at compile time, and to what extent? And the answer there is, well, maybe it'll be optimized at compile time, and yeah, probably, perhaps, but you're not really sure if it will, if it's guaranteed to be, and if so, to what extent. The reason here is that compilers are free to do what they want. Even in an optimized build, the compiler may or may not do something with this method. It might inline it, for example, but there's no guarantee that it will do what you want, which is to calculate the answer to this method call, to calculate 42 degrees in radians at compile time. Now this is where constexpr comes in. Constexpr will allow you to enforce that the result of this method, degrees to radians, will be calculated at compile time, and at runtime, when the code is compiled and when the code actually runs, the code that it is actually run will only contain the value that is the result of this method. So the runtime behavior will be exactly the same, because answer, the variable answer, will contain exactly the same value. But degrees to radians will never actually be evaluated at runtime, because it will have been replaced by the compiler with the result of the expression. And the way that you can enforce this or guarantee this is through constexpr. So let's have a look at this. So I have here a brand new command line application that I'm just going to use to demonstrate this. We have a method here, degrees to radian, that we saw on screen earlier. Pass in a double, and it will calculate the radians for that. Now, how do we ensure that this is calculated at compile time? Well, there are a couple of steps. First is we can call it. So first of all, let's just call the method normally, and we compile that. We'll see if that works. And this is straightforward, normal C++ code. We're just invoking degrees to radians, and at runtime, most likely, depending on the compiler, this will actually be called. This method will actually be called and invoked at runtime. Well, the first step is to say that this method can be a constexpr method, so it can be evaluated at compile time. Now, if we compile now, we'll still compile fine. Do we have a guarantee, though, that this method will be evaluated at compile time? Well, not yet. What we need to do is ensure that this expression is a constexpr expression. And at this point, we now have a guarantee that at compile time, the value of rad, of the value in radians, will be evaluated at compile time, not at runtime. So if we run this application, what we will see is that at runtime, degrees to radians is never actually called. In fact, let's have a look at that. And we'll look at the CPU view. You can see here that although we have a line that is rad equals degrees to radians, we are never actually stepping into a method. We're not jumping or calling or invoking any method at all. Thus you can see we are actually not invoking degrees to radians at compile time. We have the value already calculated. So that's fantastic and it's really useful, but you might wonder what happens if you don't have a constant value. Because of course if you don't pass in a constant here to degrees to radians, then you can't necessarily evaluate that at compile time. So let's ensure that we have an unknown double value. So we have a double D, and depending on the result of a random number, might have a value of 0.3 or 0.7. And the answer is yes. Degrees to radians is still a perfectly valid method. If we make the entire expression constexpr, so it is a constant expression, you will see we get a compile error. Constexpr variable rad2 must be initialized by constant expression. Now degrees to radians D, where D is not a constant that's available and known at compile time, is not a constant expression. However, by removing constexpr, we can still evaluate the method. And if we have a look at the code for this, you can see the assembly code here looks quite different, and we are in fact invoking degrees to radians at runtime. For obvious reasons, constexpr code can be limited. For example, you can only use literal types. In a C++11, you could only have very simple methods. There was no way to have an if statement, for example. Now that's been added since then. So in the C++ compiler in 10.3, you can use what's called constexpr if. Constexpr if allows you to have an if statement and discard one of the sides of the if statement at compile time. So let's have a look at that in practice. So here we are back in C++ Builder. I'm going to demonstrate something different. Let's get rid of degrees to radians. And let's have two simple variables, an int with a value of 5 and a pointer to that int. Now let's suppose that we want to get the value of either I or pi, and by value we mean the actual integer value, in this case 5. How do you do that when you could be dealing with either an integer or a pointer to an integer? In other words, we want the code here that I've just uncommented. We want to get the value of I and get the value of pi. We have some rather nice code here. Now, the C++ standard library heavily uses constexpr, and it comes with a large number of useful utility functions and that kind of thing, which can be evaluated at compile time. One of those is pointer. So you can pass in a type here in this template method, and you get a Boolean result. Is this a pointer type or not? So this is where we can start using something like constexpr if. Because we have a template method getValue with a type, and we can say, okay, if it is a pointer, then we want to dereference the pointer and return that. If it's not a pointer, then we just want to return the passed in value itself. And that's exactly what this method does. GetValue, and we have a value lowercase t of type uppercase T, and we say, at compile time using constexpr if. At compile time, if it is a pointer, then dereference that and return the pointer to value. Otherwise, if it's not a pointer, then just return the value. As you can see, this compiles fine. And this is a really neat example of using a logical if statement in a compile time evaluation. Now here's another example of using constexpr if. Let's suppose you have a simple structure called foo, and it has a couple of fields. And for whatever reason, you want to get the first or the second member of that structure. Since you're using auto, the compiler will automatically deduce the type, but you know that you want the first or the second one, the first or the second field. How do you do that? Well, in the past you would have had something that would have been extremely complicated. Using constexpr if, you can now write much simpler code to let you achieve the same thing. So we have a small method here called nth member. Now this again is a template, it takes an int, and the int is the nth member. It is 0 if you want the first, or 1 if you want the second. Now at compile time, you can evaluate the value for n, and you can say, okay, if n was 0, then I will return foo.a. Otherwise, if n was 1, then I will return foo.b. Now this is evaluated at compile time, and the values of the if statement that do not match are discarded, meaning that when you pass in 1 for this template, only this branch of the constexpr if will actually be evaluated at compile time. This is really neat, really powerful. You can do a whole heap of different things here. There is some famous code out there of someone who wrote a ray tracer using only constexpr. You can achieve a lot using compile time code. The key thing to remember is that you can consider constexpr as a way of guaranteeing certain behavior occurs, at compile time for a constant expression, and it's a fantastic way to optimize code. Optimization is one use case. This example here of the nth member is actually an example where that's not the goal, but it's very useful for optimization to ensure that a calculation occurs at compile time. Of course, the fastest code is code that never executes, and if you have a result of a calculation available to you, and that never has to be calculated at runtime, that is the fastest possible code for that value. Overall, a really powerful feature that's heavily used within modern C++. This has been a really light introduction to it. I highly recommend that you investigate constexpr further. The next one, let's have a look at something called structured bindings. So here's the problem. Sometimes you want to return multiple values from a method, such as a success value as well as more information. So you might have a logical pair with a result and a string error. So how do you do that? How do you return multiple values? Well, one way, of course, is just to have a parameter to the method that you can write back to. But if you actually want to logically return multiple values, then you have an easy solution in C++. You will say, aha, I'm going to use a tuple. So you can see some code on the screen. AutoF returns a tuple of bResult and str error. Now from that tuple you can then get some of the values, and if you remember back to the constexpr example just a minute ago, std_get here will look like a familiar code snippet. You can use that to get the boolean and string values out of the tuple. That's a little ugly, so let's change the problem definition. You want to return multiple values from a method, and you want to use them easily, not bound inside a tuple. Aha, you will say, I can use std_tie. And there's a code sample using std_tie on screen. Here we declare two variables, result and str error, and we tie, use std_tie to place the values that the tuple contained inside those local variables. But that's still rather ugly code. I mean, it's 3 lines of code to be able to handle the multiple return value from f, and you can't use auto or other type inference. You have to know that you're getting a boolean and a string. So change the problem definition even further. Sometimes you want to return multiple values from a method, and you want to use them easily, not bound inside a tuple. And just repeat, really want to use them easily. Aha! This time you can use structured bindings. This is the same 3 lines of code written using structured bindings. The key bit is in bold, where it says auto, and then in square brackets bResult str error equals f. This is a beautiful line of code. What it does is it creates 2 local variables, exactly as though you had declared them yourself. Both are bound to the tuple results, simply in order. bResult is the first item in the tuple. Str error is the second item in the tuple. And both use type inference, using the auto keyword here, which of course makes it much simpler. You should be using auto heavily in your C++ code. Here, one of the particular advantages is that you can change the tuple that's returned very easily. So that was a super quick overview of structured bindings. At least a very natural code, and you can use local variables. Here's a slightly larger snippet where you can see that you can use bResult and str error exactly as though they are normal, locally declared local variables, because that's what they are. Structured bindings can be used in other ways as well, but I think this is one of the neatest, and I think one of the best ways to sort of conceptually get what they do. It's a really neat feature that's been added. It's just sort of syntax sugar. It makes something that was already possible easier, and leads to much more natural code, much shorter code that does what you expect. One really nice thing, of course, is that you're using type inference as well, so you get all of the benefits that comes from that. One of the other nice things in C++ 14 and 17 has been the increase and expansion of the use of the auto keyword. So C++ 11 introduced auto, which was type inference for variables, and we saw this in the previous section just as something assumed, but let's have a quick look at it now. You can see some code on the screen. Auto A equals true. That declares a variable A. The compiler will infer that the type of A should be Boolean, because the expression is Boolean. For the next line, auto b equals foo, then b will be whatever foo returns. And you can use that for something like a range-based for loop. So for auto it colon mymap, where the colon there is the syntax for using a range-based for loop, it, the iterator, will have the correct type automatically. So this has quite a few benefits. One of the big ones is that C++ used to be very verbose. For example, if you wanted to iterate through a structure like a map, you would often have to type a really long line of code for the iterators. So using auto there reduces a vast amount of typing. And the other thing is that by reducing the amount of typing, in fact by removing the explicit variable type completely, it really helps refactoring. And when you type something like a really long type name, then you get stuck with it. Refactoring can become more complex and harder than it should be. Whereas when the type can be inferred by the compiler, then you can change your method to behave differently, to return different type, for example, and then all the variables that interact with the return type of that method will just automatically pick up a new behavior, and that greatly increases the refactoring speed. Of course, when code is easier to refactor, it's easier to improve. But in C++ 11, type inference here was only for traditional variables. And there's a logical question. If a variable can have its type deduced, why can't you deduce the return type of a method? Such as the code on the screen, autofoo return 5. Why isn't that valid code? Why can't the compiler decide, well, okay, obviously foo is returning an integer? Well, that's exactly what you can now do. So let's have a look. I have two methods here. The first is a traditional method that returns an int. And sure enough, it declares that it returns an int, and then it returns one. The second uses the fact that the auto keyword can now be used for a return type. So I call this method return something because it's up to the compiler to decide exactly what it returns. In this case, because we return 1, that's an int, and return something will have the return type of integer. I invoke both these methods here. You can see using uniform initialization syntax, and both I and j will be type inferred to be integers with a value of 1. Those are quite simple methods. I have a very simple class here just to demonstrate that you can use auto. What has the potential to grow to a much more complex method. Something like find employee might return some kind of complex employee type, and that would also be completely okay. But here's a question. These methods look pretty straightforward. It's really easy to tell, looking at them, what the method returns and so what type it is. What happens if you have a method with multiple branches and it tries to return something that could be confusing? Well, here's an example of a method like that. So this method here can return -1 or can return pi. Will this work? How is the compiler supposed to interpret this? It returns an integer or a double. And you can see that that is an error. The specific error we get is that auto and return type was deduced as double here, which is correct. 3.14.59 is a double. Deduced as double here, but was deduced as int in an earlier return statement, where this would be the earlier return statement. It's a pretty straightforward and I think easy answer to the question. If a method has multiple return statements and those return statements are not compatible, or rather the inferred type for both return statements are not compatible, then the compiler won't know what to do. But there's more to auto. Here's a completely different question. What about lambdas? What if you wanted to make them more generic? A lambda function is really useful because it's a small localized function object. Here's an example of some syntax for a lambda function that you can now do on screen right now. Auto add things equals bracket, auto a and auto b, and it returns a plus b. Now note that nowhere in there is the actual type of either a or b specified. Well, what this means is that you can use the same lambda with any type that supports operator plus. For example, you can have add things 1 and 2, where those are integers, and add things hello and world. And the lambda there will be compiled and work correctly for both types, as long as they have operator plus. So now let's look at the final section. This is the miscellaneous bit, the random hodgepodge section. So I thought, while I'm giving this sort of fairly light overview of a few new C++ features, I might as well look at some interesting English words as well. For those of you who've never come across the word hodgepodge, hodgepodge means a random mixture of all sorts of different things. It also happens to mean, and I didn't know this until I actually looked it up in the dictionary to create this slide, it also means a kind of stew. But I've always used the first definition, which is just a random collection of things. So with that said, let's have a look at a hodgepodge of fairly random new C++ features. The first one I want to look at is something called if-init, or an if statement with initialization. So in the past, you might have code such as the code that's highlighted on the screen. So you declare something and you initialize it, you give it a value, and then you check it and you do something with it in an if statement. Now this is verbose because it's an extra line of code that you might not necessarily need, and it's also potentially unsafe or dangerous code because it leaks the variable p outside the scope of the if statement, and if you only want p to exist within the scope of the if statement, that can be potentially dangerous. So if-init achieves exactly the same thing, but you can declare and initialize a variable inside the if statement itself. I've highlighted some other code on the screen. Here you can see the same thing. If int pointer p2 equals get pointer, and that declares the variable p2 and initializes it. p2 is scoped only to the if statement, so it only exists within the if statement itself. That's safer because then you can't accidentally use it outside the if statement. Now, of course, an if statement has to be implicitly Boolean, but we have a pointer here. Pointer, of course, is convertible to bool, so we don't need any explicit Boolean expression. If you have something using some other type, such as a string, this is an example of using if-init with a string. So if string s equals getString. Now, a string is not implicitly convertible to bool, so we need to have a statement within the if statement that is a Boolean expression. So this here allows us to declare a variable s of type string. S will be scoped only to the if statement. It's initialized, and there's a conditional, a check, all within the one line of code. So it's much more concise, shorter to write, and of course it is tightly scoped as well. Also have a few more random C++ features. You can now declare nested namespaces. So in the past, with this bit of code here, you would have had to write namespace foo, and then inside that namespace bar, then inside that namespace z. Now you can just write namespace foo : bar : z. Another example is the use of inline variables. So this behaves exactly like an inline method. It can be defined identically. So with an inline method, you'll get a copy of that method, perhaps located in many places, but will behave as though there's just one. Here an inline variable behaves exactly the same. It will behave as though there is just one of them. There are some new attributes. One I particularly like is the noDiscard attribute. So this means that the value that is returned from this method must be used. It's quite common to call a method that returns something and then to not actually use what is returned. Sometimes that can be a coding error. Perhaps it's an error code that it returns, and if you have good style, then you will check the error code, but you forget. Sometimes it might even do something like allocate a resource. It will return a new pointer. And of course, if you don't do anything with the return value, that's a memory leak. The noDiscard attribute here gives a compiler message if you don't use the return value. A couple of other things. Optional has made it all the way from Boost into the standard library. So you can now use std optional. Optional is a container that may or may not hold a value. You can check if it has a value or not. A couple of other ones such as std variant, which is a C++ version of a union, std any. All of those are worth checking out. You may already be using them or very similar classes. They're now part of the standard library. So there we go. This has been a really quick and I think quite light overview of just some of my favorite new C++ features. We looked at constexpr. Constexpr has existed since C++ 11, although it's been expanded since. We have excellent support for that in our new C++ compiler. One common use case, and the way that I prefer introducing constexpr to people, is to use it for compile time optimization, in other words, fast code. Structured bindings, again, a really useful use case for it is for unbinding complex return types to local variables. Auto, which is a fantastic feature introduced in C++ 11, has been expanded to method return types. And it's really good because you type even less. Of course, using auto for variables, you will type less as well. And it really assists refactoring. Auto is now also a keyword that you can use for generic lambdas. So these small, lightweight function objects are now easily reusable. And of course, there are a bunch of miscellaneous useful things. So that's some of my favorite new C++ features. All of them are available today in C++ Builder 10.3 Rio. So download RadStudio 10.3 and try it out. Now I'll move over to Q&A. Just while we're doing that, there are some links on the screen. Most of them are links about what's new in RadStudio 10.3, which came out a couple of weeks ago. On the left, inside the blue rectangle, there are 2 links specifically about C++ 17. And I would suggest you follow those. They contain other links to other resources as well to learn about a whole lot of new features and new items that are in the language. And with that, let's move over to the Q&A.